Don Dingwell m'a autorisé à faire la présentation en français. Donc vous connaissez Don qui nous visite, qui est là encore pour quelques semaines et qui reviendra l'année prochaine, je pense. Donc il est professeur à l'université de Munich et il est professeur en volcanologie expérimentale. Donc l'intérêt du séminaire aujourd'hui, c'est de nous expliquer ce que c'est que la volcanologie expérimentale. Alors je ne vais pas le présenter plus longtemps, je ne vais pas faire la liste de toutes ces médailles et de tout ce genre de choses et de ces 300 publications. Donc je lui donne la parole. So, Don.
Yeah, thank you very much, Mark, and continued best wishes to you in the coming years at IPG. So I'm here for a few months working with Daniel Neuville, trying to do something new on melt inclusions, which is not easy because there's been so much old good stuff done on melt inclusions. But at the very end, I will say one or two words about what it is that we're trying to do. So what I'm going to do now, many of you will know that I've been responsible for a reasonably large group for many, many years. And so what I'm going to do is tell you about a large team effort of many components which collectively, I think is beginning to have a major impact in the way we understand how volcanic processes take place, and also, and very importantly, the implications that knowing how volcanism takes place has for understanding the fluxes that volcanism is responsible for in the Earth system, for the material that volcanoes contribute to the Earth system, and for the implications that may have. So when you see me getting down into the details now of some aspects of what happens on a very short time scale in very violent volcanic events, you can enjoy it, you can be entertained by it, but hopefully it will also be clear to you that it can have consequences for how volcanism contributes to the Earth system itself. Because that's the grand hope, that all of this is useful in a broader context. So the first slide is basically my pitch to you, which is to remind you that these eruptions that we're dealing with, these continual contributions from the lithosphere to all of the other spheres that you see there, is a fundamental part of the Earth system from the very beginning, perhaps much more prevalent in the early part of the Earth's history. We don't know that with any certainty. And of course, it's rampant throughout the solar system, as we now know. All of the histories of the terrestrial bodies of the solar system are massively impacted by volcanism. The most spectacular recent example was the flybys of Mercury, with the observation that indeed the expectations of people like Jim Head and others who had modeled Mercury and Lionel Wilson had inferred that you needed a great deal of volcanism on Mercury, were confirmed by the morphological observations and the remote geochemical observations of the surface. So volcanism is everywhere, and we should view it as our constant companion, if you will, throughout Earth history. And sometimes it's easy to forget or to ignore or to diminish the significance of what it's capable of doing geochemically, but always remember that in whole Earth evolution, it is the melts that generally do the job. They are the fantastic transport agents of heat, of energy, the fluxes of material, and ultimately the differentiation of the Earth itself as a body is taking place in the context of a liquid host. So it's all related. The problem is better known at IPG than it is in most places that I speak, so I'll quickly skip over a few slides that many of you will have already seen, just to remind you of the global distribution of these things. It's very easy to be distracted by the fact that plate tectonics made such a great contribution to where we see volcanoes. But of course, that is a very imperfect description of where we see volcanoes. There are lots of volcanoes which are not essentially contributed to by the distribution of plate boundaries. So volcanism is something that's happening all over the Earth. It is impinged on and impacted by the presence of plate boundaries. Of course, the great engines of flux of volcanism are along the constructive and the destructive plate boundaries, but they're in other places too. So the Earth is leaking all over the place its own liquids onto the surface. Of course, jumping from the sublime to the detailed, it's also something which impacts us on potentially hourly, daily, or weekly basis. Just had to be reminded of the strike of Lufthansa pilots yesterday, which caused me to fly in this morning instead of yesterday, to be reminded of what flight disruptions do to us. And of course, we all recall the great flight disruptions of the Eyjafjallajökull eruption, which was a small eruption in Iceland, but of course, which made the whole business famous for a few weeks in Europe until it's forgotten again and other problems come along. But it's going to happen again, it's going to happen continually, and it can also be global in magnitude. We have the examples, the recent examples of Chilean volcanoes causing temporary shortages of airports in New Zealand. The problem is also from a risk point of view well known to many of you in the room. This is just one of the most dramatic demonstrations of the complexity of the issue of risk in association with volcanoes, and it's certainly not complete. It's imperfect, it's impartial, it's not complete. There's more to the story. But look how much is already in the story. So obviously, what the hazards are capable of generating in terms of risk is something that brings in a wide range of expertise in mitigation. And in turn, that demands a wide range of expertise applied to solving the problem of estimating the hazard potential and therefore the resultant risk. And of course, my angle on all of this, I'm trained as a petrologist in Canada to look for gold mines. I mean, I don't come from the field of volcanology. I never had a proper education in volcanology, and that explains a lot of what you're about to hear. But our basic approach, as I'm sure you all know, which was conditioned by my 12 years in Bayreuth, is that I'm an experimentalist. And so what I've tried to do in my career is add the third leg of the stool, as I would say in English, the third leg of the story to modern volcanology. I wasn't the first. I came a generation too late. There were many experimental volcanologists before me, but we've added a particular kind of experimental volcanology which I think has complemented that which went before, and which has also brought to home the major point of experimental volcanology, and which I would argue is you start with liquids, you end up with rocks. This is going to be complex, liquid to rock. So in the same way that plate tectonics struggles with the brittle ductile transition as one of the great outstanding questions of the mobility of material in the Earth, we do exactly the same thing on another scale when we talk about how volcanic liquids become rocks. And that's where our contribution has added to what went before and added to the purely fluid dynamic analysis of these events and added in the rock physics of these events. Now, this is the big business of volcanology. This is where all the money goes, or 99% of it goes, and I encourage everybody who's involved in this, including several in the room, carry on. It's great stuff. We will only ever be as good as the observations, of course. And the fantastic thing about volcanic systems is they're close enough to the surface that you can, relatively speaking, in solid earth sciences, you can get enormous amounts of information out of the system. It's really an exciting place to work. And there are new methods being applied as each passing year occurs. But the greatest challenge of these systems theoretically is greater than the practical challenge. The practical challenge is to get enough instrumentation and enough sophistication in the instrumentation to have real-time monitoring of chemical, geodetic, and geophysical systems in sufficient quantity with sufficient resolution. That's an enormous challenge which will eventually be conquered because everybody recognizes it as the first challenge of volcanology. But the second challenge associated with all of this is, what do all the signals mean? And how do you attempt to understand what the systems mean? You have essentially two possibilities. You have simulations, forward simulations, which can generate signals, which are equivalent to those which are observed in nature. This is performed, for example, by people like Paolo Papale in Rome, who is working on generating models of magma mixing and the signals which are fed downstream from those results. The other thing you can do is experiments. You can see if you can actually generate seismicity in the laboratory. You can see if you generate degassing in the laboratory. You can see if you can understand the deformation which is involved. So a long time ago, in a place far away, I drew this picture, and it's in German. I've been funded by Germany for 30 years, so that's my tribute to that. Basically, it's something we don't believe anymore. It was a useful approximation once, which is the idea that there is a linear sequence of events which lead to a volcanic eruption. We think now that these events, these different physical processes, saturation, nucleation of bubbles, growth of those bubbles, foaming, and fragmentation, you can see English is a Germanic language, we think that these events are overlapping and that there may even be cyclic transfer between these regimes, such that this material on the way out, especially in dome building eruptions, probably has an incredible story to tell of how it eventually arrives at the surface, such that you may move up in this diagram, drop back down, move up a little again, drop back down, and you may have a really complex story of the material which is being finally accessed at the surface. But in terms of experiments, of course, what we try to do is take each one of these events, strip it down to an experiment where we have absolute control over what has just happened, and then observe what the experiments yield for us. And a key feature in my personal approach to all of this business is represented by this diagram, which is nothing more than a reproduction of what is called the glass transition. And now you see why we're also very conversant in the glass literature, because the quantification of that yellow line is basically the business of making good glass. And so it has been worked on extensively for almost 100 years in the glass industry. And essentially, if you want to make good pressed glass bottles for Coca-Cola, you have to know how to work with that yellow line. It's as simple as that, okay? We made the claim, myself and Sharon Webb made the claim back in 1989-90, that this is also a line which is crossed when explosive eruptions take place. It's a very controversial claim. We think in the meantime that we were right to have claimed so, and we think that we've been able to prove it to a good extent. The basic point is that these flowing liquid materials at high temperature, what I mentioned earlier, are ending up as solids. And if they have not fully crystallized, and that is often the case in volcanic flows, in volcanic ash falls, and so on, then the material which has not crystallized is a glass. And you've gone from liquid to glass, and that is the definition of the glass transition. So the question now becomes, okay, I know in principle what just happened. What good is it? Can I quantify it? Can I put it in its place? Can I tame the uncertainty associated with where this takes place? Can I measure it in rocks that I obtained from volcanoes? So just to remind you what many of you already know, these things going from liquid to solid have many expressions of that effect. This is one example of going from liquid to solid. If you look at that out of focus, you see a large plastic mass. But if you focus in on the details of what you can see, you see blocks of semi-solid material falling off the front of the flow. So the simple observation of a blocky lava flow is the absolute explicit definition of something crossing from a plastic, something which has the properties very close to those of a liquid, to something which has the properties of a solid. Now, in the case of Etna, it's a question of how much glass is left in that blocky material. But in other cases, it's even more spectacular. And of course, these are the now quite old pictures of the collapse of oversteepened domes on Unsen from the early 90s,
something triggers a
which resulted in tragedy.
About 10 times bigger than all that came
and this
before.
is just to remind you that what you're looking at here
it overwhelms the valley.
Is also the glass transition occurring. Because those materials were moving plastically on the dome. but they were no longer moving plastically when they collapsed and started to head down the mountain. So you've lost that degree of deformation in the plastic continuous state. You've gone into the fragmentation state, and you're just about to see the cloud, as many of you know this in your dreams because you've seen this video often enough. But of course, the hazard potential that's associated with these things is also related to how these things fragment. And you'll see this video stop as if it was just cut with a knife when the driving, there you go, when the driving force of this thing stops. So how do we try to quantify both sides of this yellow line, and how do we try to understand what happens at this yellow line and demonstrate to you, try to convince you that it's important? First of all, if we're looking at the fluid behavior of such systems, it's all really about the rheology, because the rheology is what allows the material to flow better or worse, depending upon a lot of factors. And rheology, together with perhaps one other geophysical parameter, electrical conductivity, is one of the most spectacular variables in earth science, right? It runs over tens of log units of value. So if you're somebody who wants to see big changes in order to get excited about your work, rheology is one of the places you can work, because you can literally in laboratory with these two pictures cover, for example, 12 or 14 log units of the property being investigated. And of course, if you do that, you begin to see simplicity break down. This is just a sketch of the variation of chemistry of natural liquids as total alkalis versus silica in the upper left. And on the lower right, corresponding to each color of the composition in the upper left, you have a set of two segments of the temperature dependence of the viscosity of the liquid. And you can see as a general feature, they're all curved. They're no longer linear in reciprocal temperature space. That we say that they're no longer Arrhenian. And over the course of a couple of decades, we built up enough of a data set to finally be able to give a robust and reliable multi-component model for calculating the ability of these liquids to flow as a function of their chemistry and their temperature. It's basically chemistry and temperature. You're looking at temperature. If you can transfer the colors in your mind, you're looking at chemistry, okay? People often ask me the question, pressure? And I will tell you in few words, pressure basically doesn't matter. It's a small effect, okay? So it's all about temperature and chemistry to get these spectacular ranges. That's a log scale on the lower right, from 10 to the minus 2 to 10 to the 14. The glasses are formed in the upper right of this diagram, typically in nature. And because the original models of viscosity were not particularly interested in glass formation in volcanoes, it was probably viewed as a detail in previous decades, all the concentration was on the liquidus regime, which is the lower left of that lower right diagram. And so what was added in the recent decades was the upper right part of the diagram, which demonstrates to us that we cannot extrapolate from lower left to upper right. We need both sets of data. What I just showed you are so-called Newtonian viscosities. That means it's unique values for the rheology of these systems for any given chemistry. There's many other ways to describe it. There's physical ways to describe it. There's thermodynamic ways to describe it. But let's just say that these are the rheologies of the materials which are strain rate independent. That's the simple empirical definition of a Newtonian viscosity. And if it's strain rate independent, it means that the time scale of deformation doesn't matter, which means that you're looking at something which can be extrapolated to long time scales. And almost everything which is done in solid earth geophysics experimentally is extrapolated to long time scales. It's often extrapolated to low frequencies from high frequencies. For example, all of the mineral physics of elasticity of crystals, which is typically measured on small samples at megahertz to gigahertz frequencies and extrapolated down to seismic frequencies, which are 6 to 9 log units away. So this whole business of timescales is essential for solid earth sciences. But in experimental volcanology, we can remove ourselves from the problems of extrapolation of timescales because we can actually do things on volcanic timescales. That's a huge advantage experimentally. And what you're looking at here is looking at the collapse of this approximation of the rheology being Newtonian. If you try to deform these materials too fast, then you will see that they no longer maintain their strain rate independent response. They begin to literally collapse structurally. It's quite a remarkable thing to realize that you are literally, by deformation, pushing physically the liquid out of its thermodynamic equilibrium. It's a remarkable concept, yeah? But of course you can do it. If you overload it with stress, you destroy the structure of the liquid, and what you see as you go to the right here is the collapse of the viscosity, as a crystallographer would say, loading up defects in the structure of the liquid. A liquid physicist would not describe it that way. I'm neither a liquid physicist nor a crystallographer, so I put it to you in very simple terms. You literally shear these materials out of existence. So now I'm going to take you on 2 quick trips through the glass transition, and I've simply described them as fast and slow to make it as crystal clear as I can. And we'll start with the fast stuff, okay? So we're going to go through the glass transition, and we believe it is the way that volcanoes also go through the glass transition. So the way that we do it fast is with explosive experiments. And what we do in order to make these materials disintegrate is very simple. And in volcanic eruptions, it is the great constant of volcanism. It is unavoidable, and that is decompression. Because the definition of volcanism is the exposure of these materials at the Earth's surface. They are always under decompression. You can argue back and forth about the thermal history immediately preceding and during a volcanic eruption. There are also heat sources and sinks because there are phase transitions. But you can't deny the fact that everything which is coming out of a volcano is being decompressed, okay? So it's all about stress and how you get rid of it. So what we have here is a big vertical tank. We call it a fragmentation bomb. We used to call it a fragmentation bomb. We don't call it that anymore. We call it a fragmentation autoclave. And what you see is a large stainless steel tank at the top, which is basically our atmosphere. That's where we will catch everything that happens in our experiment. And at the bottom, and you see it blown up on the right-hand side of the diagram, is a hydrothermal bomb, which has been adapted. It's got a fairly large diameter. And this hydrothermal bomb is under pressure and temperature and contains a magma, a real magma, okay? At the temperature and pressure of a dome. And when we decompress quickly between the magma chamber and the upper tank, which is sitting at 1 bar, then we can lead to the generation of volcanic ash in the laboratory. So we can make our own ash every morning, and we can actually change what we do with the ash. We can change the properties of the ash. Of course, we can change the chemistry of the magma. We could change the grain size of the ash. We can do a lot of things with it. We're basically able to generate reproducible amounts of ash where we know precisely how we made it, what it's been through, and therefore serves as good starting material for any experimental studies of volcanic ash. Because going out into the field and pulling volcanic ash in large amounts, no doubt, but nevertheless of sometimes a dubious history, is more difficult. The volcanic ash which you will get, which has been distributed some distance from the volcano, has been through a lot. And it's also been through a lot after it was fragmented. I'll come to it later in the talk. So here we have the ability to obtain pristine volcanic ash from these experiments. And in the upper right, you see what success looks like in these experiments, which is this completely dirty plate, lower plate covered with volcanic ash. So this is just a sketch-up of the experiments. Some people find these things very hard to look at, but I just want to say what I just did. You have a bubbly magma below, you have a low-pressure air column above, and you basically decompress and allow this air, this low-pressure column to descend through the sample as a fragmentation front proceeds. And now I'm going to very quickly give you 3 aspects of these fragmentation experiments, the fast transition. I'm going to say something about what we call the threshold. I'm going to say something about how fast it takes place. And I'm going to say 1 or 2 words about the role of degassing during this process. Degassing, in a way, is the whole story of volcanoes because it's the gas pressure which delivers the energy for the explosive eruption. And so if you have other options for removing the gas, you don't need the eruption. And of course, that's what's happening all the time, everywhere. Literally. You know? There is no volcano which is not degassing, no volcanic center which is not degassing all the time. In fact, you can look at volcanic eruptions as failures of the degassing system. You can look at them as industrial accidents of the Earth factory. Now I'll show you a couple videos just to make perfectly clear what happens to these samples when we decompress them. What you're looking at is cold experiments because we're doing it in a plexiglass bomb so you can see through the bomb. But when we do them in the real experiments, we do it under steel bombs, high pressure steel, and therefore you can't see them. But just for purposes of visualization, here's what happens when you take the pressure off a dome rock. And some of you will have the immediate reaction, doesn't surprise me, it's destroyed with subhorizontal cracks. Yeah? There was a certain direction to the cracks which occurred because we're removing uniaxially the pressure off the top of this. If we do it with a material which is slightly less viscous, then we can begin to back ourselves into that fluid regime, and that of, excuse me, getting trouble here, getting my video started. This is analog experiment, but we're on the verge of doing this with real high temperature magma as well. That's what we hope to do in the next 24 months. And what you just saw happen in that experiment is that material was also fragmented by decompression. And now if I'm lucky and I speed up the video, here we go, you see this material has a property which is quite different from that on the left, which is when it hits the bottom here, you have the evidence from its deformation that it's like spatter. It's still got a certain degree of plasticity. And of course, this happens in nature too with low viscosity liquids, basaltic liquids. So we can do all of these things. And on the right, although that's analog, we think that we will be able to do that in the next 2 years on real high temperature volcanic liquids. So that's what happens to the high pressure tank. And here's what happens above at the same time. That is the gas being released into the low pressure tank. And here comes the pyroclastic column. This is a high-speed video, so you're looking at a couple milliseconds in total here. But what I'm trying to do by showing you this video is to convince you that this is a quasi-steady state experiment, which means that you can do all kinds of determinations of the dynamics of it, and you can try to make physics out of what's going on. So when we talk about it, it's a bit controversial. When we use the word explosion for explosive eruptions, if you say it to anybody who's not a geologist, the first thing they do is think about the old idea of a chemical explosion, right? A detonation, which is something which was an idea, as you probably know, in the earth sciences a long, long, long time ago, and died a couple hundred years ago. So although these things are explosions, they are not instantaneous. Please never use the word instantaneous with respect to volcanic processes. It happens all the time. It's always wrong. Things take time. You just have to know the time scale. And the time scale is very important. So here you can get individual particle trajectories. You can get flow properties. You probably, if you were looking at it while I was talking, and I hope you were, you could probably see that there were pulses which were associated with it, which have to do with the dynamics of the geometry of our experiment. That's what we're doing. What can we quantify? Very simply, we know that we need a certain amount of decompression before that happens. That doesn't happen if I take 1 bar of pressure off of a volcanic rock. It's not enough. And the amount that I need to remove is the vertical axis here. And as you see, it runs up to a maximum of 35 MPa, 350 bars. So that's the maximum, if you will, dynamic tensile strength of these volcanic porous materials. It's not much. It's a lot less than you usually used to thinking about if you're worried about deforming the upper mantle or something like that. It's much, much more, right? You see also that it's a function. It's purported here to be a function of one variable. You can decide with the legend whether you're convinced that that is one curve or many, but it's pretty damn close to being one curve. And what you see in the legend is, if you know volcanic systems, is that there's everything in there, chemically speaking. We have everything from basaltic andesites all the way up to rhyolitic liquids in dacitic dome rocks. What it's telling us is, this is physics, it's not chemistry anymore at this stage. This is about the physics of breaking rocks, and the strength of these materials is similar. even though their viscosities are wildly different, but viscosity doesn't play a role anymore. It's too late. So we can describe this part of the volcanic system purely using the physics of fragmentation of these materials, and it's directly related to the porosity because the porosity gives us the potential energy of the stored pressure in the bubbles. And that's the energy which drives this explosion. Prior to this kind of development of a threshold of fragmentation, which may seem absolutely obvious to you, I apologize if it does, it wasn't absolutely obvious in the discussion of volcanic fragmentation, and the typical assumption that was made was that you needed a certain value of porosity to generate through-going fragmentation. And that value of porosity was somewhere up there in the yellow band at a very high value of porosity. Well, you can break anything. I guess we sort of knew that. It's just a question of what it costs. How fast? The answer, slow, quite slow. Volcanic fragmentation is not a fast process. These numbers, I don't know if they appear to you to be fast or slow, but just compare them in your mind to seismic velocities. These materials responding in a rigid state so they can give you elasticity at all are characterized by seismic velocities very similar to other rocks, several kilometers per second. And yet the process of disintegration of our materials by fragmentation is between 100 and 10 meters per second, okay? So the acoustic waves are passing through these materials far faster than the disintegration is ensuing. It means that we need a significant amount of time to excavate, remove, erode, use whatever phrase you like. And in fact, the velocities become so slow under certain circumstances that they start to reach into the range, the upper range of what we speculate to be ascent velocities of magma from great depths, from kilometers depth, okay? This is a very exciting observation because it may mean that you can stabilize fragmenting explosive eruptions over days or weeks as we observe simply by matching the velocities of supply and disintegration or removal or excavation. This is one of the simplest ways you can imagine that you can stabilize something which you're nominally calling an explosion. We have many videos which show that these volcanic systems blow out jets of pyroclastic material over hours and days. And how can we sustain something like that? Obviously, it has to be something which is balanced or in phase with itself such that the system can develop a steady state. And so seeing two velocities which can possibly agree with each other, the input and the output, if you will, velocities, is a very, very exciting observation. Now, of course, we also see volcanic eruptions that go bang, and that's it, and it's over. So there are situations where we do not have sustained flow. And so in such a case, one would have to infer that the supply rate was minimal or was negligible compared to the eruption rate, compared to the erosion rate or the excavation rate, right? We do have that. You even have that in rock bursts, in coal mines. I mean, that's just an explosion of overpressure in rocks, right? So we do have the case where the supply velocity is insignificant. I think we also have the case where the fragmentation velocity is insignificant because we also, of course, have domes which emerge at the surface and somehow have avoided producing pyroclastic clouds at the phase, or major pyroclastic clouds at the phase of dome erosion. We have rhyolitic lava flows. So we probably have regions where the velocities are not in step with each other on one side, which produce domes, regions where they're not in step with each other in the other direction, where you produce Volcanian explosions, which leave holes in the ground, or even phreatic explosions. And in the middle, where the big ones are, where we get the greatest fluxes out onto the Earth's surface. Think about supervolcanic eruptions and the amount of ash that they produce. I think there you must have these matching velocities. All speculation at this point on my part, simply due to the numbers we get. But it shows the value of doing the experiments and getting the numbers, otherwise you would not know whether you're in the magnitude of the playing field of this kind of discussion, this kind of conversation. Nobody would have predicted those numbers beforehand, nobody of whom I am aware. This is the last point I want to make about these fast experiments, and that is that as you go in permeability from impermeable to permeable, from the left to the right, in the lower right diagram, you start to see something which is invariant with respect to permeability, and then it becomes dependent on permeability. If this experiment, fragmentation experiment, is dependent on permeability, then it means permeable flow, significant permeable flow is taking place. Degassing is taking place during our experiment. And of course, if we go to the right far enough, we will push the permeability so high that it must play a role. But if we go to the left, we suppress the permeability enough that it plays no role. And so therefore, you have the invariance. No role. On the right, high permeability, a variance. It plays a role. So we actually know now in permeability where the gases essentially can degas and can outrun, in the event of a decompression, can outrun the need for fragmentation. And there is no fragmentation. You see? So we begin to focus in on where this malfunction of the system takes place in terms of rock physics. Very exciting. Okay, a few steps through the slow transition. Just to remind you, there's lots of observations and lots of reasons why you would want to do this slowly, because nature also does this slowly. It does this slowly in the case of dome extrusion, which is roughly sketched in this diagram, where you go from a liquid or highly plastic interior material to something on the surface continuously connected to that which is in the interior. It's one material, yet the surface, if you walk across the top of a dome, people actually do that sometimes, or if you send a drone, which is the way I would recommend, it looks like the top of a glacier. It's like a calving glacier. It's fragmenting away. So in the same way in glaciology, people study the rheology of the glacier, and yet you have fragmentation and calving. That's the best analogy I can give you, something you're perhaps more familiar with. Same thing is happening in volcanic dome building eruptions. So this is a very slow process. And of course, it's very seismic, this process. As you probably know, in terms of number of events, volcanoes are one of the most seismic places on Earth. I had to be careful. I'm not a seismologist. There's a lot of noise out there, I know. There's a lot of noise out there as well. But there's a lot of seismicity on our planet. Nevertheless, 400, 500 events a day is no problem for an active dome-building eruption. And you can make simple estimates of repeat times of these events from the observations of seismicity associated with them. These things have been called various things in various places. One of the expressions which I think describes it most beautifully is drum beat seismology or seismicity. Okay? So you can imagine your volcano is coming out, is extruding, and is doing that at a few hundred meters depth. Yeah? And the big question becomes, how can it do it again and again and again at the same place? It's obviously not brittle rock which is failing, because once it's failed, it can't fail again in the same place. And this led us to the conversation about whether it couldn't be the magma which is failing and then is rehealing and failing again and rehealing and going through a cycle of stress buildup, stress release through failure. Sealing because it's still a liquid. Stress buildup, stress release through failure. Sealing because it's a liquid, and so on and so on and so on. So when we cross this transition, we know at least in principle that we have three problems to deal with. We have viscous heating, which is sort of hanging around waiting to influence our experimental observations. It's a very tricky business to deal with viscous heating. We have the structural effect of the collapse of liquid structure that I show you in the middle there. So these things are going to shear thin, even if they're pure liquids. Even if a rhyolite is extruded with 95 or 97% glass, that material was still capable of shear thinning under the wrong or the right circumstances. And that's the effect in the middle. And then, of course, and as a general rule, we have the suspension effects. We have the fact that we have up to tens of percent of porosity in terms of bubbles, and we have up to tens of percent of crystallinity, which are certainly inviscid particles, which will complicate the rheology of this description. So we try to pick apart these effects. This is where experimental work now really comes in to its own and gives you an added advantage. To distinguish all of these things by observing a rhyolitic lava flow in nature is a noble thing to try, and people are beginning to try it now. But it's a huge challenge because you don't have the direct observations of the interior temperature of the flow. You don't have the direct observations of the vesicularity of the interior of the flow. In experiments, we have a chance because we can characterize these very viscous systems absolutely before an experiment. We can do the experiment, and we can characterize them absolutely after the experiment. And when you have a very viscous system, the amount of deformation and the amount of phase redistribution is under control. It's not going anywhere too quickly. And of course, the frontier, as I will say a little later, is now, today, we can actually characterize them fully, texturally, during the high temperature experiment through tomographic analysis with synchrotron-based sources. So the frontier, which is ripping open right now, is that the multi-phase rheology and multi-strain rate rheology of these systems will be characterized in situ with observation of every single crystal and bubble of an observable size, which is going to revolutionize the way we model lava domes. What you see here is a big uniaxial press. On the right-hand side, you see before and after samples of a standard material. You see 3 big steel pieces going into one of those samples. Those are sheathed thermocouples, and we literally compress that that cylinder from its original height down to this slightly barreled shorter height, and in doing so, we measure the temperature increase. Here we've done it with the dome lava. You can probably immediately now get a feeling for whether or not you think that this is a representative through-going deformation of the sample, which is, in this case, multi-phase. And we can measure the very, very subtle temperature increases due to viscous heating in these materials in situ during deformation, basically under the conditions of deformation in the Earth. The same rates, the same temperatures, and because we're dealing with volcanic domes and flows, which are basically at the surface of the Earth, under the same pressure. So we're as close as you can possibly imagine to getting to the actual deformation environment in nature. And what we discovered is that there are 2 different boundaries which cross each other, one of which implies that first you will get viscous heating, and the other of which implies first you will get structural collapse of the liquid. And these 2 results could not be more different, because in one case, viscous heating, you push yourself away from fragmentation. You push yourself away from the catastrophic event of destroying the rock, because the temperature increase decreases the viscosity of the liquid. And so you basically avoid the catastrophe. And in the other case, you're observing the catastrophe through the structural collapse of the liquid. And so the idea that you may go from one regime to the other at a temperature of about 600 degrees Celsius, where that green line crosses that blue line, gives us the potential of a remarkable playing field of these events in nature, because this temperature of about 600 degrees Celsius is something which we would see near or at the surface of these flows in nature. Okay? These things are seismic, I've said it before, and so our experiments are seismic if we want to take the trouble to measure it. And so we measure it with acoustic emission sensors. And you can look at the statistics of acoustic emissions. And if you look at the left-hand side of the diagram, you have the time, and then you have the amplitude in decibels on the right-hand scale, and then you have the number of events or hits, which is showing you how events ramp up to a catastrophic failure, both in terms of amplitude and in terms of the time scale of deformation. And so on the right-hand side of the diagram, at the top, you have 3 different values of the stress sustained by the sample as a function of the different loads that you see listed up there. You see that the first 2 are leveling off to a viscosity which is constant. In the third case, the viscosity is beginning to collapse. You see a line which is going straight down to the right. The reason it's collapsing is that the viscous heating has now become significant enough. You're heating the material. Remember, you don't have to transport this heat. This heat is being generated everywhere where 2 atoms are shearing over each other, so it's actually auto-production of temperature. And so it's immediately at the place where it needs to affect the rheology as soon as it's generated. Okay, it's not being heated from without or something like that. It's not a heat transfer issue about getting the heat in. It is a heat transfer issue about whether or not you can prevent the heat from getting out, of course. But you can see also on the bottom part of the scale, the acoustic emissions, the numbers of acoustic emissions described as an effective energy of acoustic emissions, and you see that it starts to ramp up non-linearly. The fact that we can observe the statistics of what these things do acoustically in the laboratory, and we can also observe that they fail catastrophically in the laboratory, you know where I'm going, right? I mean, in principle, if we understand it well enough in the laboratory, we have at least a shimmer of hope that we can understand the equivalent seismic signals pre-catastrophic failure in actual volcanoes. Okay? Now, I know you can get into a lot of trouble in this world by talking about prediction and forecasting, and there's lots of phrases that people kick back and forth, but I truly believe that in volcanic science that we're going to make great progress in the statistics of success of forecasting events in the coming decades. Okay, I really have to move rather quickly through these slides. It's just to remind you that we get the ash, okay? We have the ash sample in our hand after our experiment. That's unlike anything else anywhere else in the world, and it means that we can make a science out of understanding how the ash varies as a function of the fragmentation event. And the most obvious question you can ask is, what's the grain size distribution of the ash? And if I increase the pressure of the decompression, does the grain size distribution of the ash reflect that change in energy of the fragmentation? And the answer is yes. We looked at various properties of the ash as a function of temperature and pressure, and you can see one example here of experimental pressure versus the weight fraction of the fine particles in the ash, and you can see a correlation between the two. More pressure, more energy, more fragmentation, more surface, finer ash. Okay? And we have the advantage that we can measure the specific surface. The devices are routine in material science. We can measure the grain size, which allows us to independently calculate the specific surface based upon particle shape approximations. You can do a lot of things with these materials. And of course, you've generated materials which you can use as input into one of the last great themes that I'll mention towards the end, which is, okay, you've got this ash. In fact, you've got it all the time. There's always a little bit of the lithosphere above your head. Okay, over Earth history, average, there's always something up there. What influence does that have on our planet? Is that irrelevant because the mass is insignificant? Or should we be concerned about the surface? Which leads you into avenues of research which are not geoscience exclusively, leads you into all kinds of chemical and biological themes, which I don't have any time to talk about today, but which are things which we're talking to people about. Okay. Let me jump ahead. I'm not going to talk about this. Let me come to what I now want to try to sum up towards the end, which is a couple of frontiers that I see beyond everything we've done so far. And here are 4 examples that I quickly want to show you. Frictional melting in conduits has now been proposed. We've suggested the phrase volcanic pseudo-tachylite. I apologize if anybody is offended, but if the more you think about it, I think the easier it is to accept that there could be volcanic pseudo-tachylite. You just have to heat something a very, very, in principle, an infinitesimally small amount of volcanic viscous heating can generate reactions going backwards, which means frictional melting. It should be easier to frictional melt something which is just at equilibrium with the liquid at the moment than to try to do it starting from scratch in an earthquake zone where you have a fully crystalline rock which you have to bring up to 800 or 900 degrees before it begins, or even more. Yeah? Anyway, that's the first theme. The second point is the cyclical treatments of this heat fail cycle that we think may be related to these drumbeat earthquakes. Not everybody accepts this explanation. Many people still want to do it with steam explosions. The third point, ash aggregation and other aspects, and the fourth point, volcanic lightning. So this is a plot. This is a diagram or a video from Jan Lavallée and Jackie Kendrick.
HVR 3.
And I apologize that it's so loud, but I can't control the volume here. What you're going to see is 2 pieces of dome rock, which are in a lathe, essentially, friction rig as they call it, and are being frictionally melted. Okay? So this is just to give you the clear and I think unforgettable impression that you can characterize quantitatively the stress that will be held in a shear zone when you have volcanic materials on both sides, okay? And this stress, of course, is something that then you can then try to take and apply, actually not only to the possibility of these faults which we see on the top of volcanic domes, but also non-volcanic faults, where, of course, pseudo-tachylite is a big point of discussion these days in trying to understand what happens in fault zones in tectonic faults. Something I know nothing about, but I'm a big fan of. These are experiments where you see two cylinders of rhyolite being brought together and then being pulled apart with various, or with increasing, if you will, time scales or dwells of being held together. In other words, as a function of the time scale of the experiment, we're trying to understand how much stress it takes to pull these things apart again. In other words, what is the effective healing time? Okay? And luckily, in material science, a lot of people have already tried to deal with these issues. Welding two things together under hot conditions is a big technological process. So we're trying to quantify, and this is work of Jan Lavallee as well, trying to quantify what is the recovery of strength as a function of time. If we crack these things and heal them, what does it take in order to crack it again, to bring it back to its original state of strength? Because that is implicit in explaining drumbeat earthquakes by this mechanism. The ash life cycle. This is one of the ugliest diagrams I've ever seen in my life. You probably think it's from the IPCC or something like that. And you probably, when you see this kind of thing on television, you change channels. I don't know, maybe you love it. But its complexity, of course, is it's incomplete. Huh? None of these things are ever complete. This is just for volcanic ash. So it's just to tell you how much science is left to be done with volcanic ash. Everything from soil development to biological interactions to the presence of the surface in the atmosphere, catalytics of the chemistry of it. It's going to be something for the next 20 or 30 years, no question about it. This is from Paul Iris and Pierre Delmel. What we've built in Munich is a reactor to try. Paul Iris has built a reactor, a high-temperature reactor, which is basically a tumbler which allows us to reproducibly expose ash to gas mixtures. And the reason he built it was he had this idea that once, and this is sort of counterintuitive, but once you've fragmented this material, you don't do it at 0 depth. You do it at hundreds of meters depth. Perhaps you even do it at 1 kilometer depth. There's even speculation fragmentation may take place at more than 1 kilometer depth. That means you're still in a tight conduit. You're still in a hot situation. You have hot gas. You have hot ash particles made primarily of glass. And these things are going to be accompanying each other for several tens of seconds at least until they can get out of the top of the conduit. And the question is, does that matter? Does anything happen between the ash and the gas after the fragmentation event? It's counterintuitive because this gas has come from the magma, which the ash has come from. It's all from the same system. But of course, as soon as you turn it into a dusty gas and decompress it, it's out of equilibrium. The speciation of the gas starts to change, and you have the potential that it will start acting, or it will start seeing its co-erupted ash as the enemy or the friend, or however you want to describe it, as an opportunity for back reaction onto the surface of the ash. And if this is significant in volcanic eruptions, then you never see a pristine volcanic ash as I would define a pristine volcanic ash, which means at the point of fragmentation. Everything is corroded, altered, adjusted, at least on a micron scale of the surface by reaction with the ash, with the gas. So is this just an idea or is it real? Paul has done a set of experiments using this device, which he built at Munich, and he's come to the conclusion, which some of you may have seen, which we gave the provocative title, Sequestration of Sulfur in Volcanic Eruptions, just to hope that more people would read it, because of course everybody sees volcanoes rightfully as a major source of sulfur. Is it possible that there is a huge variability in the efficiency with which volcanoes can release their sulfur? We have phrases still kicking around, such as the sulfur problem, the sulfur paradox. Can it be that a part of the story is A part of the story is the variable efficiency with which sulfur is recombined on the surface of erupting ash and therefore is not detected by remote sensing of sulfur that comes out of volcanoes. And Paul is convinced that that is the case, and then the chemistry begins, because then you have highly variable chemistry of the erupting liquids. You have very spectacularly per-alkaline liquids, high activity of sodium and potassium, which allow you to speculate that they might be highly reactive in the formation of sulfates. And you have others which have almost no sodium and potassium in excess. And you have different depths of the reaction front. You have different depths of the fragmentation. So we tumble these things in the presence of the volcanic ash. We look at the surfaces of the experiments afterwards. You have two issues. One is diffusive transfer into the glass phase itself, and the other is precipitation of phases on the surface of the glass. And you can now start talking about the mineralogy of ash surfaces and speculate on what the fate of these sulfates on the ash surface can possibly be. Can they simply be deposited back into the volcanic pyroclastic deposits and forgotten about, or do they ever effectively enter the Earth system reactively? Transport and deposition, of course, is the king's discipline of volcanic ash studies, because physical volcanology is very useful and very effective in being able to measure the distribution of ash after major events. And the reason we know there are supervolcanoes is because of these huge fields, hundreds of square kilometers of volcanic ash of significant thickness. So this is a very, very well-established discipline of physical volcanology, and yet the modeling of ash distribution still struggles. Physical models of where the ash goes, how much of it there will be, the complexity associated with these plumes is still a very active area of research. And in fact, when you have eruptions which contain a lot of sulfate which is coming out, and at the same time you have a lot of ash coming out, you actually can have those separating at different heights in the column, affected by different wind patterns, and we saw that with Eyjafjallajökull, that you had two different plumes going off in two different directions. So you get a feeling for the complexity which is potential here. And I just wanted to draw your attention to one detail which is just now being incorporated into ash distribution models and cannot be yet effectively incorporated fully because we don't understand the physics of it yet, and that is what we call aggregation. Watch the circles. There's one. There's number two. Do it one more time for you. This is under the ash cloud of Eyjafjallajökull as it's erupting. And if I can get it to run again, you see what happens. These are coming down as aggregates of at least hundreds of particles, and they're just disappearing from the volcanic record completely. So going out and digging out the ash deposits, as a good physical volcanologist would do and should do, is not going to show you that there was aggregation involved in the fall velocities of these particles, is not going to allow you to infer that backwards when you try to calculate the model of distribution of the ash. So you have issues, you have issues here. And once again, I believe that experiments to a certain extent can come to the rescue, because there are simple limitations of observation in the field, and there are simple assumptions which cannot be tested any other way in the simulations. Okay, I'm almost done. I really appreciate your patience. There are industrial devices for looking at aggregation. Aggregation is actually a big business all over the place. Your breakfast cereal is probably an aggregation. If you eat a dry muesli or cornflakes or anything like that, it's an aggregate. And so there are actually devices for aggregating materials. And we've had the cooperation of a company which has allowed us to put hydrochloric acid and sulfuric acid and volcanic ash into one of their devices, which would normally be used for some sort of breakfast cereal, and then to clean it afterwards. And it's allowing us to quantify, Sebastian Müller, the second, is quantifying that very nicely. Now I'm almost done. I'm right down to the last few details of applications. You know what the problem is here. The problem of ash ingestion in the turbines can be broken down, on aircraft can be broken down into at least three problems. Abrading of the windows so you can't see anything. That happens with sandstorms as well. If you've ever flown a plane in Egypt, you know you can almost not look out the window anymore because it's all abraded away by the sand. But of course, the turbines themselves have two problems. One, the turbines are often hotter than the volcano. And we have a problem here. This stuff melts in the turbine. It's as simple as that. And the other problem, of course, is that they're choking the system, that vital mixture of air and fuel is being choked by chucking in solid rock at the same time. So the way we're trying to deal with that is do what we can do well and easily first, and that is to simply look at what happens to the adhesion, to the remelting, to the wetting, and to the spreading. Now, there's 4 different things going on here. As you have liquids, samples, adhering to the surfaces, which are candidate turbine materials. And there's a postdoc in Munich funded by the Volkswagen Foundation who got a huge amount of money to study all of this. You may know that there are ash ingestion tests actually which have been done recently. So there are actually facilities where they throw everything into jet engines, even chickens, right? I mean, everything, right? Because of the hazard of flocks of birds on runways and stuff. And I don't need to dwell on this point in Paris. But the point is, there's huge multi-million-dollar experiments being done. They'll only be done in a very small number because they're huge and multi-million-dollar. And it's not as common as sandstorms. So it's not going to be, we're not going to get a wealth of data. Yeah? So our idea in doing this work was to say, okay, do your few ash ingestion experiments, spend 10 million per experiment, but then for God's sake, give us some of your material. Let us take 20 other materials and let us try to help generalize your results, scaled in temperature and in glass content and whatever it is which is important, so that we have a general model for the safety hazard which is associated with ash in the air. Now, if you talk to an engineer about this, they generally say, it's all dirt, isn't it? I've literally had that said to me. It's all dirt, isn't it? So maybe they're right. Maybe it doesn't matter. But don't you want to know for another 50,000 whether it's important or not? And so when I get that question, of course, I say to these engineers, well, I'll tell you when I've done the experiments, whether there's any significant variation amongst the materials which are erupted. Okay, and basically done. I show you the last picture, which you already know what it will be, and that is, it was a serendipitous result, one that we did not expect, but one which we stumbled on. Here you have the gas flow that you've already seen before. So that's all what you know, and then you see the lightning strikes. So these are not induced lightning strikes. These are happening, quote, by themselves, unquote, okay? Not expected, almost not observed, for years not observed, and then accidentally observed and believed to be a faulty camera, and then with a faster video, high-speed video has changed a lot in science, observed to be a fundamental feature of these particle flows. Now, near-event lightning is not a phrase we invented. It already existed. It's a very common feature in volcanic eruptions of pyroclastic flows. So every time we see something like this, an element of our experiments which matches something we see in nature, we get very excited, and we think there's one or two less skeptics out there who think that all of the things that we do are completely exotic. All of that work is now flowing into work by Corrado Cimarelli and by Masato Iguchi in Japan and others in Sakurajima, where they're actually trying to characterize the quantification of the electric field density and the drops in electric field density with the lightning strikes on volcanoes, trying to calibrate it experimentally, because the hope is that if you have a proxy for the fine fraction of volcanic ash in terms of the electric field drops, then you may be able to actually monitor what the in situ flux of fine ash from a volcano in Iceland in the middle of December, in the middle of the night, is. And it's almost impossible to do any other way. The sad truth of volcanic eruptions is that we have very little understanding of how to predict the flux during a volcanic event, whether it's explosive or even effusive. We see orders of magnitude jumps and drops in flux, and if we're worried about the downstream impact of the distribution of ash, and we don't even know the source function to the ash cloud, then this is obviously an area where we can try to improve the situation. I'm going to stop there. I apologize for this assault on your intellects with all of these different, this salad of results that I gave you. But what I tried to do, more than giving you one example of a well thought through study, is just to give you a bird's eye view of the kind of stuff which is possible with what I call experimental, I and some others call experimental volcanology. And it's not that expensive, actually. People have the impression experiments are expensive. They're not, compared to most other kinds of geoscience. And I think they have a great future. I hope you agree. Thank you.
Commence.
No matter of doubt that hash and gas are not really good friends during after the fragmentation in the column, in the conduit, and then in the column, and that part of the sulfur dioxide, as you showed, becomes absorbed and removed from the gas phase. It remains that the predominant observation in volcanology that we have an excess of sulfur dioxide. So the proportion of removed sulfur will depend on the ash proportion, the size, and for reactions and so on. But this just outlined how we still underestimate even sulfur flux emissions during major eruptions, hash-rich eruptions.
Yep, I agree. And I think qualitatively what this adds is by putting this variable in, that it may depend upon the depth of the fragmentation and the chemistry of the eruption, that you can appreciate that the variability that you see may be partly compensated by this effect. And we simply don't know yet because we don't have enough comparative examples as a function of chemistry. And as far as estimating the fragmentation depth, this is the kind of thing I should be able to tell you, but we're not far enough along that we can actually say, you know, Tambora was this and something else was that. In principle, we should be able to get there because this is a function of the decompression magnitude and so on and so forth, and the grain size distribution be related to it. So in principle, someday, somebody will do the physical volcanology field work and invert it to these kind of explosive parameters, and then you may have enough information, background information, that you can start to ask the question of whether the results on the variability of sulfur coming out of these things are reduced by this effect or are exaggerated by this effect. Absolutely.
Yes, Don, I was wondering if you had looked at the implications of your fracture healing experiments and theory on the problem of understanding how large amounts of fine ash are generated almost in situ in volcanic domes without explosive fragmentation, and therefore how you form very early on mobile and devastating paraclastic flows.
First of all, you put me in mind to say that we clearly see that even during the extrusion of of rhyolitic flows that we have ash being generated, blowing out of the surface of the flow and so on. So it appears that the generation of volcanic ash is something that goes hand in hand and accompanies all kinds of extrusive activities of these systems. So the perhaps old idea of either or, of switching, I certainly have used the phrase in my day, of switching between eruptive modes, which are either dominated by ash or dominated by dome building, is an oversimplification, right? It's more a question of the balance of how much is being fragmented and how much isn't. You know, the original work on the flow banding over 10 years ago now was the idea that there are untold numbers of these events within the conduit, which are fragmentation events, which we presume are seismic to a certain extent, and which produce ash. And the question is whether how this ash can get to the surface, whether this ash has a way out of the system, or whether it's locked where it is produced and sealed again. And of course, in tuffosites, we believe that a lot of what we see is the result of ash which has been rehealed, and the flow bands themselves, we believe, are rehealed ash events. So I think that it's really a question of the architecture of the system, of whether the ash can get out from where it's being generated. But everything that we think about this fracture-healed cycle would contribute to the feasibility of producing ash during an extrusion event. or even during no event, when the amount of material being delivered to the surface is very, very low.
Yeah, well, what I meant is not so much ash that is produced inside and then released, is the fact that when you look at a lava dome, growing lava dome, I've looked at that many times on Montserrat, flying over in the helicopter, being very close to the dome, and you see these huge masses of rock. You could see that in your video. And almost in situ, instantaneously, when it breaks down, you form immediately ash, meaning that there must be some, large number of microfractures in this rock, allowing itself to produce ash in situ and then to form a paraclastic flow. I'm not so much talking about the venting of ash in dome formation, but
okay. Yeah, you have very efficient fragmentation going on, and the efficiency of fragmentation there are several things which influence it, but of course one of them would be the length scale of whatever it is which is defining the effective decompression front within a material. That can be porosity, or it can be microfractures. We also, I'm sitting in a house which has discussed dome stability for decades here in Paris, and I don't mean to say that I know more about it than anybody else. I know much less. But we have the time scales of dome collapse as well, right, which are not completely random. They tell a story of cyclicity. And my fantasy on that is that this could be some sort of material story. That there could be something about the time that it takes to generate a certain material gradient in the dome, which leads to a fundamental instability on the outside. That's just one idea that one can put in there. And if it were something like that, then it is something which is imminently or eminently experimentally accessible to test. And there's a big discussion, of course, on the development of permeability and the sustenance of permeability in these domes, despite crystallization, despite shrinkage. I just got an email this morning from Fabian Wadsworth in Munich, where he's talking about the influence of tens of % of crystallinity on holding the porosity of these domes intact. There must be enough data accessible when one asks the right questions in fieldwork to be able to make some of these answers more precise. And I guess my prejudice in all of these things you sense, oozing out of every crack here, is that these are materials which have sufficient complexity that volcanic science is also really, truly a material science. And understanding the rock physics of these things is an essential part of understanding how they behave. So aggregation, at this stage in the game, there are many different factors which have been brought into play to discuss aggregation. Electrostatics have been brought into play. There's all the geochemical inferences that you can make, liquid-hosted drying liquids which are binding particles together. And of course, if it's a major chemical influence on the efficiency of aggregation, I don't have the impression that there was a big chemical influence on the efficiency of aggregation in the pictures you just saw. They were very weakly aggregated, disturbingly weakly aggregated. But you, of course, have lots of aggregated particles that survive, and there's a classic observation of physical volcanology that they exist. Started the debate in the first place. And so what I suspect is that in the next 5 years, that we're probably going to begin to shake out what are the big players in aggregation and what are the insignificant parts. But as you know, there have been many ansatz which have been applied to discuss the physics of aggregation, which stand somewhat in opposition to each other as to what the driving forces for aggregation are. If it turns out to be a chemical effect of basically cementing this material together, then we're going to have to work our way through the potential variability of the chemistry, which is in the gas phase of the ash which is being aggregated. And that'll take a bit of doing. Now that's going to take figuring out the sulfates versus the chlorides and so on and so forth. And that's what Paul Iris had been doing for the last couple of years. It's being carried out further by a young student named Ana Casas with our device. But we warmly welcome a bigger community to work on aggregation. If you don't have aggregation, how can you do distribution? If you don't have distribution, how can you predict risk from ash clouds? And now the first models build it in, of course. Now people claim that they do aggregation. Of course, this is the danger. But we don't have the physics and chemistry of it sorted out yet. It's the classic quandary of the experimentalist, right? Is that everybody wants the answer, they want it now, and if you're restricted to doing forward models of simulations where you define all the physics, you can produce the simulation results on a fairly quick time scale. But of course, the experiments can't be done that quickly, and that's why we're often looked at by people who do simulations as, with impatience, I would say. It's just the way it is.
Okay, so thanks again. So, no, Patrick.
Going back to to decompression rates and fragmentation. On it, we measured during 8 lava fountains, successive lava fountains with infrared spectroscopy, Fourier transform infrared spectroscopy, that the most violent lava fountains were characterized by higher chlorine to sulfur ratio release compared to less powerful fountains. We interpreted this as due to possibly faster diffusion across smaller particles. Do you have any experiments that could, do you perform experiments or do you have programs on calibrating not only diffusion rates but degassing rates from particles as a function of decompression rates?
My prediction is that it will be done in the next couple of years. We made a start trying to do it by getting in fact there is an unpublished PhD thesis which you probably will never see, which has the diffusion rates of chlorine, fluorine, boron, and iodine, which are quite different, which gives you the chance, the hope. I talked to Benoît Villemont years ago about this as well here, and gives you the hope that if you have a good budget of the halogens, for example, of all 4 of them in the glass and in your observations of degassing, and if you have the diffusive calibration and you know the partition coefficients, then you can play with the idea that possibly you have diffusive fractionation of halogens during degassing of the volcanic system. And that's what I would hope to try to accomplish. I'm also talking to John Castro about it at Mainz, and we've just written a project on looking at differential halogen degassing. Absolutely. And the microanalytical techniques now will give us enough data from classes. Yeah.
Ok, donc on peut continuer la discussion dans la médiathèque, si vous voulez. Il y a un pot qui vous attend. So, thanks again.
Thank you. Thanks very much.